One of the things I would like, hopefully, to get across to everybody as we're going through these review problems is to show you what I'm looking for, what are the AP test graders looking for, what do you get points for, how should you show your work, that kind of thing. It's about communicating what you're doing. So even though this is a calculator problem, there are certain things you have to communicate of what you're doing. It's easy to just start typing stuff into your calculator and then just write down an answer and then not get full credit for your thought process. So you've got to communicate what it is you're doing. So if you're plugging 5.5 into these two equations, this is a really easy thing to write down that communicates what you're doing. So I'd like you to kind of get in the habit of this notation when you do this. So on one of these, I can't remember, velocity was what? Negative, somebody got it written down? 0.4534, okay. And this was negative 1.3585, okay, whatever. So 8, 9, you don't have to round, you can truncate, doesn't matter. But essentially those. So the fact that they're both negative means speed is increasing. Speed is increasing. Now, they're the same sign. So that would be your reason. So I think that's probably about 3 points right there. One for each of those and then your reason. So you really, if you just wrote down the velocity and acceleration are both negative, so therefore the speed is increasing, I don't know. I mean, maybe the graders would give you that. You know, I graded the AP test one year, and they're kind of picky on things, but they're not looking to dock you points either. They're looking for good mathematics. If you've got good, good rationale, good communication, good mathematics, it might not be exactly the way they were thinking it should be. They're looking for ways to give you credit. But if that's all you wrote, it makes it tough. And so I think you should write this down, okay? The things you do in the calculator, somehow communicate what it you're doing. Now, Brenda, you said look at a velocity graph. Tell me what you saw on the velocity graph at 5.5.
It was negative and had acceleration was also negative.
In other words, it was negative and going away from the x-axis. It was negative and getting more negative. So when you say the acceleration was negative, you know the slope, right? But remember, we talked about that. If the velocity is going away from here, negative and getting more negative, this thing's speeding up. Or if it's positive and getting more positive, that would be good too. If you said that the velocity graph, and maybe even drew a quick little sketch of it, you know, at 5.5, the velocity graph is negative and decreasing. That would be enough. That would be enough to say that so the speed is increasing. All right, so that's good. And that's another way to look at that one. All right, let's go to number 2. All right, number 2 would be, it talks about the average rate of change. Well, isn't that just slope? Or excuse me, approximate rate of change at 3.5. That would just be the slope between these 2 points right here. 3.5 is halfway between 2 and 5. Show the computation, so that'd just be 52 minus 60, 5 minus 2, it comes out negative, right? The temperature is decreasing. That's all that would be, right? That's all you would have to do then. All right? 3a. Write the equation of the tangent line. It is so common. You know, think about this. The AP test has half of the grade on the AP test is a 6 free response questions. So those 6 free response questions have to really cover a lot of material. And they cover the big main ideas we have in calculus. And every year, you're going to see an equation of a tangent line somewhere, maybe more than once, in the free response section. You're going to see a position velocity acceleration problem, for sure, as one of the 6. Today, we're going to talk about differential equations again. You're going to see a differential equation problem as one of the 6. All right? So equation of a tangent line. Well, we need 2 things. We need this point, and we need the slope. Okay? So I hope this was just a really easy one. Here's f right here. So you plug a 1/2 in, 1/2 cubed. Now, this is no calculator. 1/2 cubed is 1/8 times 8 is 1. Do the derivative. 24x squared. Put in 1/2. 1/2 squared is 1/4. 1/4 times 24 is 6. Write the equation tangent line, point slope form, 6 x minus 1/2 plus 1. Equation of tangent line. Right? Need the point, need the slope, and x equals 1/2 of the f graph, and away you go. Okay? Probably a couple of points on that one, maybe 3 even. All the free response questions are worth 9. So they always have to decide how many points it is. So even though I graded them once, I have a decent understanding of how they grade, but you never know for sure how many points. And as we go through this process, I'm going to try to teach you about that. I'm going to try to say, hey, they look for this, they look for that. I want you to communicate this. But in the end, I don't think you should really worry about it. I don't think you should be thinking, oh, I wonder if I get a point for this, or should I do this? I just want you to get in these habits so it's just automatic. You don't have to think about it. You can just work out the problems, and then your stuff will be there. Okay? Like units. Sometimes these problems have units. Should you put the units? I think you should always put the units. Do they give points for the units? Sometimes. Sometimes they don't. It depends on if there's enough points to add up to 9. If they need another point, they might throw in a point for units. If they don't need another point, they might not. Now, to be honest, they usually are pretty good with their directions. If they're going to give a point for units, a lot of times it'll say, be sure to include units. I mean, they actually, they're not trying to trick you, and I'm not either. All right, so let's go on. We did number 4 yesterday. Number 5 we're going to come back and look at here in a little bit, which I did not assign you yesterday. But we've certainly seen a problem like this before. What do you do to show f is continuous? Put 0 into both of them and set them equal to each other, or see if they're at least equal, right? This one says show that it's continuous at 0, right? Sometimes we had to find a value of k that makes them continuous or something like that. But here we would just have to show. So how would you show? Well, what I would do is actually write it out. I would put in the 0. And then I would put in the 0 in the other one. Actually write that. And so this side you get 1, e to the 0 is also 1, and so it checks, that kind of thing. So you put in a 0, show that their outputs are the same, it is continuous. So good, we're on track with that. We've done that. Now, B's a little trickier. Write f prime as a piecewise function. Now they said for x not equal to 0, so we don't have to include the 0. Well, so that's just do the derivative. Piecewise function. Derivative, what's a derivative of 1 minus 2 sine x? Negative 2 cosine x. And then I would put out here x less than 0. You wouldn't have to include it because they said x won't equal 0. And then it says, and then the derivative of this one. Negative 4 e to the negative 4x. And that's when x is less than 0. Okay, so that's the first part of this. Express f prime as a piecewise function. That's it.
It's greater than 0.
Oh, yeah. I think did I say greater than?
No.
I said less than?
Yeah.
All right. So x is greater than 0. All right, now find a value for which f prime is negative 3. So what do you think? Set them both equal to negative 3. Now this is a no calculator problem, so you go into that and you think, ooh, that's going to be ugly. Well, maybe not. You get this. When does cosine equal 3/2? Cosine has to be between negative 1 and 1. So it cannot equal 3/2. So that's no solution there. All right? Set the other side. Negative 4 e to the negative 4x. When does that equal negative 3? So divide both sides by negative 4. We would get positive 3/4. Then what? Natural log of both sides would give you negative 4x equals the ln of 3/4. Divide by negative 4. I would rather write that as a negative 1/4 actually in front. I just think that's better. You wouldn't have to, but you would get this. Now, you actually can't just stop there. Or shouldn't. Actually, it turns out in this one you could and you'd be fine if you gave this as your answer. But what should we really check on that? Positive. If it's in the ring. Right. Because we did it with this one. And this is only when x is positive. So if this is a negative number here, then we would have to throw it out. Okay? It's got to be positive to be within this range. So is that positive? Without a calculator, you need to know that yes, it is positive. Why is ln of 3/4 negative? because it's less than 1. Now, let's say that isn't making sense to you, then you should think of a graph. I think thinking of natural log, one of the things that they really are good at when they make up these questions, and these are the kinds of questions that I use for the midterm and for our final, and a lot of times on our quizzes too, but they're good at embedding within problems other knowledge from pre-calculus kinds of things. Like in this problem, you had to know some trig right there to do this part. You've got to know about LN in this part. Okay, so not only the calculus stuff, but they quiz you on these other things you're supposed to know as well. So here's what you should know about LN. Well, e to the x, we talked about inverses the other day. There's e to the x, goes through 0, 1. ln x goes like this. You should all have the ln x graph memorized. This is when it's useful, because you know that this is 1 right here. So what's ln of 3/4? That'd be back here. It's negative. So ln of 3/4 is negative times negative 1/4. That is a positive value. So therefore, this is an acceptable answer for that range or for that domain. And so that would be your x value answer for part B. Okay. It didn't say explain. It just said find the value of x. So if you had that answer, if you worked out through that answer, you'd be fine. Okay. But it's possible it could have been one we had to throw out, and if you had that for an answer, you'd have missed that part. Okay? All right. So, good review, good stuff as far as putting together things we've learned in the past. Now, set this aside because we're going to come back to number 5 and talk about some things with it as we learn some stuff here in chapter 4. All right? So, go ahead and get your notes out. All right, we're going to be starting here in about page 211 in your book is kind of in that vicinity is where we'll be at. You might want to go ahead and get your books out because we will be referencing some stuff in the book here, and the calculators will get used here at some point along the way too, just to show you something that your calculators are capable of doing.
First, differential equation. What's an equation?
This is what I'm afraid of. Art,
He's gonna die early.
we did take some shortcuts before Thanksgiving when it came to differential equations. Some things we just didn't quite have time for. I said we'd be coming back and getting into that a little more later on, and that is kind of now. All right. So just to review some of the things we talked about with differential equations. All right. First of all, a differential equation is an equation with a derivative in it. Right. So it's got a y prime or an f prime or an h prime or whatever. Okay. It's got a derivative in it. So that's a differential equation. And the tricky thing about differential equations was the solution. What's the solution to a differential equation?
An equation.
Another equation, the original equation or the original function. Sometimes it's not actually even a function. I probably shouldn't say function. I probably should say equation or relation because it's not always a function. So if your differential equation had y prime, then your solution is a y equals equation. If your original function had w prime, then your solution is a w equals equation. And if your differential equation was p prime, then your solution was p equals, and so forth, so on. Okay, and so that was the thing we had to get across. Now, we did all those problems with verify. Remember our last quiz? We had to verify that something was a solution, did the T-chart kind of thing, that kind of stuff. All right, we talked about 3 different types of differential equation. The first type was one that we can solve. Matter of fact, when I asked in the other class, when I asked what the solution to a differential equation, the first thing somebody said was antiderivative. Well, not really. The solution to differential equation is the original function. One way to find the original function is to do an antiderivative. So one technique for solving differential equations is just do a straight antiderivative, which is what we do in number 1 here. Y prime equals 3t. Antiderivative would be 3 halves t squared plus c. Right? There's always some constant in there when we do an antiderivative. So when the solution to a differential equation almost always has some unknown constant in it that we have to then find. So that would be ones we can solve. Now the reason we can solve it, it has just t in it, or x. If it just has the input variable in it, then we can just do an antiderivative, because it's with respect to t, or with respect to x. The second type we said, and I don't remember what order we did these, but the second type would be ones we could memorize. Now I've got 2 of them listed here. Okay? This one on the left was one that I gave you last time, and then now there's this new one on the right. So the one we had last time is y prime equals k times y. Notice that's the y, the output variable there, not x or t. That's different than number 1, where we can solve them. If it's the output variable, it's a different story. That was the old PERT formula, or an exponential function like bank interest. Exponential decay. If k is negative, it'd be a decay. It'd be an exponential curve going down. Okay, if k is positive, it's a curve going up. The new one is this over here. Now we had that in our last quiz. If you remember, I gave you one like this. It was like a hot coffee cooling in a room, right? This is actually called Newton's law of cooling. Newton's law of cooling. If k is negative, it'd be cooling. It'd be going down. All right? This was the differential equation for that. So it's similar to this other one. And look at the solution. It's very similar. It's actually just the other one shifted up by capital T, which is the room temperature. So if you think about it, if coffee cools, it comes down and it levels off right at room temperature, just be shifted up. A normal e to the x function levels off down at 0. This would level off, shifted up at the room temperature. Okay? All right. So that is one we're going to have to memorize and recognize as well. And that's the one we're going to focus on here in Chapter 4. So you can pretty much bet on the next quiz, the one next Thursday, there's going to be a problem, something about Newton's law of cooling. Okay, it should be an easy problem for you because of the practice we'll do in working those out. You'll have opportunities, let's put it that way, to make sure you know how to do that. Okay, we'll get to one of those here a little later. And the third type is ones that we don't know how to solve. And one we don't know how to solve is probably going to have both y's and t's in it. Or just y's. I mean, it could have just y's. If it has just y's and it's not one we can memorize, then, of course, that one we're not going to be able to solve. But if it's got a mixture of x's and y's, then we're in trouble too. Okay? We'd have to take a course in differential equations to solve most of them. Later this year, we'll learn how to solve a few. Okay? But it'll be a select few. All right, so that is stuff we've already kind of talked about with differential equations. All right, what we're going to do today is we are going to investigate something called a slope field. A slope field. Okay? A slope field is a graphical approximation to the solution of a differential equation, DE. It's a graphical approximation to the solution of a differential equation. The solution of a differential equation is the original function, y. So this is a graphical approximation of what y is what this is saying. A graphical approximation of what y is. All right. Now, over on the board here, which somebody in the video will not be able to see. All right. So if I gave you, is it working?
Yep.
If I give you this graph right here of f prime, okay? I would say to you that we have done this, sort of. Because think about it. If I give you an f prime graph, isn't that kind of like a differential equation? I mean, it's not an equation, but it's, what's an differential equation? An equation with a derivative in it, right? It's like starting with an f prime or a y prime. And we want to solve that differential equation, means we want to do what? Find y, the original, or f. So it's like starting with an f prime graph and wanting to draw the f graph. Have we not done that? Chapter 1, right? We did that in chapter 1. So when we were doing that, in a sense, we were solving the differential equation. It was an approximation, right? Because it was not a very accurate drawing. I mean, mine weren't real good either, you know. But it was just rough. So it was an approximation. Now, let's practice that. So this was f prime right here. So we want to draw f. So where would I start? We don't know, right? That's that whole plus c thing. So a lot of times in these problems, they gave you something like this, right? An initial condition. Now remember, I didn't have that in the notes earlier, but remember when we did in chapter 2, differential equation, we talked about IVPs? Initial value problem. We didn't make a big deal about it. It's one of the things we shortcutted a little bit. An initial value problem has an initial condition in it. It's a differential equation with an initial condition. So when we were doing that, that's what we were doing. We were doing initial value problem. We didn't know it. We didn't call it. So that gives me a starting point. So that tells me I'm going to start at the point 0, 1. And now where's my graph going to go? It's going to go up because this is positive, right? Now up how? Concave down. It's positive and getting less positive. So it's going to go up like this. Now, we talk about how accurate this is. We talk about being an approximation. How accurate is that? How confident do you feel that, you know, if I had labels on this axis and tick marks, that point is where it's supposed to be?
6.
Six, seven. That's pretty good. I wouldn't be that confident. But you know what I mean? I just went like this. I had no idea if I was going up, if it should have went up real steep or, you know, because I don't have any numbers here. Now, if I knew this was a 1, right, then I could have been a little more accurate. I could have said, oh, okay, that's where we got the speed limit law, right? I could have said, oh, the slope starts out at 1, so when this goes up, it should have went up not quite that steep. It should have been going up only kind of a 1 slope, right? So I could have really investigated these numbers a little more and then saw how steeply it was going. And that's kind of where a slope field comes in a little bit. It's a little better approximation than what we did before, but it's kind of, it's connected. All right, so let's keep going. So now it's negative and getting more negative, so this thing's going to go down until there. That's going to be your inflection point. Then it's negative and getting less negative, so this is going to come down and do that. And we're going to have a local min right there, and then it's going to go up a little bit, right? So that would be a reasonable approximation of what the f graph is. But I don't have a lot of confidence that if I wanted to know f of 7, right? They told me f of 0 is 1. If I wanted to know f of 7, I don't have a whole lot of confidence. If this is 7 here, I don't have a whole lot of confidence that that's where f of 7 is, right? I mean, because I was just sketching. So I feel pretty good about the shape of this, but I don't feel real good about what those values are necessarily. Okay, so what the slope field is then, what the slope field is a way to do this, make this a little better. Okay, so let's take an example here. Let's do this as our differential equation. Let's do y prime equals, go ahead and you guys write this down. We'll do this together. So let's say my differential equation, so we'll start with an easy one that we actually could solve. Okay, y prime equals 2t minus 1. Okay? And what I want is a graph of y. Okay? I want to solve the differential equation. I want the graph of y, the original function. All right, so here's what I'm going to do. I'm going to put a few tick marks on here. 1, 2, 3, negative 1, negative 2, negative 3. We'll see here. Okay, and this could go up here as well. All right, and so here's what a slope field is. And I'll get some red. All right? A slope field is this. The only information I have is y prime, which is a slope, just like over here. This told me when it went up, went down, if it was concave up, concave down, that kind of thing. So since I have an equation now, not a graph, I can actually plug some numbers in. So I could actually do y prime of 0. I could actually plug a 0 into this differential equation. And what would you get out? -1. What's that tell you about the y graph? Its slope at 0 is -1. So that means I don't know where the y graph is, because remember we talked about that earlier, but I know that if the y graph goes through here, if t is 0, I know it's going to have a slope of -1. It's going to be doing that. We call those slope segments. We call this a slope column. Okay? Those are little slope segments. If when I draw the y graph, when it goes through t equals 0, right, which is the y-axis, it's going to have a slope of -1. Does that make sense? All right. Let's plot another point. Let's plot a 1. What do you get? 1. So when t's a 1, I know that this graph is going to have a slope of 1. I don't know where it is. All right? I don't know where it is for sure, but when it gets to that point in the graph, it should be going up with a slope of 1. All right, let's put in a 2. What do we get? 3. So over here at 2, so that's quite a bit steeper. Those should all be the same. They don't quite look the same. All right, and we can kind of tell what's going to happen as we go out here to 3. It's going to get steeper yet, right? They're going to get quite a bit steeper. So let's do one more. Let's go back to -1. Now notice I'm plugging these into the differential equation. When I plug into the differential equation, because that's all I got, I plug into the differential equation, I get slope information. All right, I put in -1, what do I get? -3. So back here at -1, I'm going to have -3 slope, which again is steeper. Now, I don't have a lot of, I mean, I could come in here and plot some that are even steeper yet, because they would be steeper, and then these would be steeper, but positive up here. Okay, now when you just look at that, maybe you have to squint a little bit to look at that. Do you see the y graph in there? Looks like a parabola, right? If you would just go with the flow and kind of follow these lines, it looks like there would be a parabola in there. And sure enough, if you did the antiderivative of this, it would be a parabola. Would it be t squared minus t plus c, right? And we don't know where it is. Now, if I was to give you an initial condition here, let's do this in black. If I would have given you an initial condition here, say y of 0 equals -1, right? An initial condition would have told us to start here, and then you could have just went with the flow. You could have said, okay, it's got to go like this, but then all of a sudden I see it turn, so somewhere here it must turn and go like this, and now I could just kind of follow those slopes, and now they're going up, and then they're going up steeper, and over here it looks like they're going up, oops, they're going up and steeper, and that wouldn't be real accurate, but it would be more accurate than this, right? And I feel a little better about this solution curve by following those slopes. And so the red thing there is called a slope field. The little slope segments make what's called a slope field. Now, we're going to draw a few by hand, not today's homework, but tomorrow. I got a worksheet. We'll do a few where we sketch them like this. Now, keep in mind, some differential equations just have t in them, so I plugged in t values. Some differential equations have y in them, so you would plug in y values. And some have x and y in them, so you'd plug in both x and y to get your slope information, okay, and get your slope field. And they can look really kind of interesting. But what you get is kind of a picture of the shape of the solution. So it's it's a graphical approximation to the solution. All right, go ahead and get your calculators out, and let's try them on there. All right, so we go into our scratch pad here. Go to our graph screen. Now we noticed one of the things yesterday when we updated is our graph is now at the top of the screen, not the bottom for our entry. Now we're going to go into menu, and under graph entry, we're going to go down to number 7, differential equation. Okay, and we notice that this changes quite a bit here. So we got y1 prime. I think you can even change that y1. I've never done it, so I'm not quite sure. I'm not sure there's any advantage to doing that. So this would be y1 prime. Now notice that it says x and y1 here for your initial condition. So that tells you you have to use x in your difference equation. Remember, parametric we had to use t. Function mode we have to use x. Differential equation we have to use x. So our differential equation was 2x subtract 1. And we won't put in our initial condition yet. Hit enter. Now that's not a very good one. I think if we change our window, it'd be a little better. So let's change our window. And let's go -3 to 3. And the y we can probably leave the same. There we go. That's a little more interesting. And you can really see the parabola there. I'm kind of curious on the settings here in differential equation mode. If we get, that doesn't really give us any. That doesn't give us any thing interesting. What about the window settings? Did I miss? No, nothing really there either. Let's go back into this. Let's go back into this. I think there's some settings here. I think you can tab to get to these different settings here. And I think, oops. Oh, that was bad. I want to get to this one right here where it says edit parameters. Oh, that's all pretty good. I'm not sure we can change that much to make that any better. So we'll just leave it there. Now, to be honest, we're not going to use this much in our graphing up. It's kind of nice to see that it can do it and so forth, but a lot of what we need it for is probably not that useful. Now, let's go into our let's hit tab and open that back up again. And let's go into our initial condition down here. And let's put in 0, and then tab, and then -1, which is what we had earlier. And hit enter. And then it puts in that solution curve. And notice it doesn't connect the dots because it's not actually doing an antiderivative. It's not actually calculating the function. It's just plotting points. It's just, and it's using a method called Euler's method, which we'll learn later on, of how it's actually calculating those points using those slopes. Okay? But you get a sense of what you're looking at. Okay? So that's what a slope field is. So let's turn to your book now at this point. And turn to page 2, I think it's 217. Page 217. This is problem number 7. Now, one of the things that you will have to do on the quiz, a couple things that I can tell you right now, you're going to have to probably sketch a small slope field, and you're going to get practice at that tomorrow. you're going to have to be able to match, which is what these exercises are that are going to be your part of your homework for tomorrow, be able to match these slope fields with the differential equation they go with. So look at the bottom of page 217, you have a list of 10 differential equations there. And on page 217 and over onto page 218, you have a series of graphs, like 8 graphs, I think. You have to match the graphs with the differential equation they go with. Now let me give you a couple of tips about how to do this. It has to do with plotting points. Okay? So, for example, an easy one to plot is 0, 0. Okay, right here is the point 0, 0. So let's just go to the very first differential equation, Roman numeral 1, down at the bottom of page 217. You got y prime equals 2t. So put a 0 in for t, you get y prime as what? 0. Does it look like y prime is 0 right here? Remember, this is the y graph you're looking at. No, it is not 0, so that eliminates that one. Now, are you going to have to go through all 10 of them and plug in 0, 0? Well, that'd be one way to do it, okay? But a better way here would be, so you could keep going. You could put 0, 0 into each one of those until you get, what's that look like the slope is? Looks like the slope's about 1. Now, what'll happen is there's probably about 3 of them in there where the slope is 1. So then you can pick a different point somewhere and see if it matches up. But let me give you a little tip here. Do you notice how this slope field, when you go across, the slopes don't change? There's like a slope row here where the little slope segments are the same. Now, how'd that compare to the one we drew? It was more of a column. It was up and down. So the one we did, now remember, the differential equation we did earlier had just a t in it. So every time I plugged in a t value, an x value, I would get a slope that would be the same for that whole x value, all the way up and down. So what do you suppose that means on this one? This is the same for each y value. For every y value you pick, you get the same slope. Or another way to think about it is as you go across to different x values, the slope never changes. So that means there must not be an x in this differential equation. It must only be y. So we did an example that only had an x in it, or a t, and the slopes were the same going up and down, or going vertically. Here, the slopes are the same going horizontally. So this must be one that just has a y in it. So that eliminates about half of them right there. Okay? Well, now look at the next one. Number 8. Oh, number 8 looks like the one we did earlier. Go to number 9. What do you notice about this one? At this y value, the slopes change. At this x value, the slopes also change. What's that tell you? It must have an x and a y in it. You see what I'm saying? So there is no row or column where the slope stays exactly the same. So right there, you can make some choices about what differential equation must match with. So that eliminates some. And then to find exactly which one it is, you plot some points and you see if the slope you get in the equation matches the slope that you see in the graph. So be able to match differential equations with their slope field. Okay, so be able to draw little ones, which we'll practice tomorrow. Be able to match them, which is what we're doing now. Okay, last thing we have for today is some work with this Newton's law of cooling. All right, so let's work on that now. Newton's law of cooling. I don't think it's anything he came up with. I think it's more just named after him. Cool guy.
That was really weird.
Yeah, all right, yeah, that's sad. All right, so Newton's law of cooling, which we had wrote earlier, which is one of these we're supposed to really just kind of memorize. That is the differential equation. Now, for our work, if we have any problem about liquid cooling in a room, we just know this is a differential equation we're working with. And since we're memorizing the solution, we can go right to here. So the work that you do with Newton's law of cooling is really not even calculus related. It's really just working with an exponential equation and being able to plug in numbers and solve and do that kind of stuff we did way back in Appendix E at the beginning of the year. So I'm going to let you try that and see if you can make this work. So here's what I'm going to give you for this problem. So we're going to say that we got a hot cup of coffee in a room. I'm going to tell you the initial temperature is 190. I'm even going to write it in function notation to make it easier for you, hopefully, to know what to do. So I'm going to tell you the coffee starts at 190 degrees. Now, this is a 70-degree room. So what is that?
Yeah, big T.
Big T. So it's a 70-degree room. The coffee has 190 degrees at the start. Now, let's talk about some of these constants. Big T is 70. A is just, A has to do with the initial temperature. It's not the initial temperature of the coffee, right? Back on that bank interest problem it was, but it has to do with the initial temperature. K has to do with the liquid that's cooling and other things that will affect how fast it cools. Like what kind of cup it's in. What are the insulating properties of the cup? What are the chemical properties of the liquid? Okay? So to find K, we need more information. We need more information about how fast it's cooling. So I'm going to tell you that 3 minutes later, it's down to 175 degrees. That should be enough information to help you find K. So you have enough information right there to find A and to find K. I haven't given those to you, but using that information, using this function, you can find it. All right? And then the question I want you to answer, so it's a little bit like what we were doing up here. Differential equation, we got an initial condition. We actually have two initial conditions. And then we wanted to find another value on that original function. So I'm going to say, after 3 minutes it had cooled to 175. I want you to tell me what it was after 6 minutes. All right? So go ahead, work with a partner if you want. See if you can, see how far you can get in this. If you're not sure where to start, find somebody who does. But I'll give you a hint. It has to do with plugging in numbers. And you can use your calculator to solve any equations that you need. You can use your this will be a calculator problem. So you can use the menu algebra solve feature to get decimal answers, okay, and use that. That'll be fun. right, anybody have a K value yet? As a decimal? Yes, no? Shout it out. 445. Good enough. 1 something. 1 0. Okay. All right. So since we know that, I mean, it's all right here, guys. I mean, this tells you when you see y of 0, what should you think? When you hear y of 0, what comes to mind? Well, yeah, that's you're even beyond what I'm thinking. Forget this problem. I just tell you y of 0. What do you think? F of 2, h of 7. What do you think? It means you plug in a 7, right? Y of 0 means you plug in a 0 for t. So you just go to this equation right here, which is the y equation. You plug a 0 in for t, and you better get 190, right, as your output. Well, what's k times 0, 0? What's e to the 0? 1. That's a wonderful thing, right? 0 is a great thing to plug in. E to the 0 is 1. That gets rid of that. You got a plus 70. You subtract 70. You got a is 120, right? So now you plug that back in. So now you know that a is 120. So you know this is 70. So you now know this is 120. So what now? Now you got another condition. Plug in a 3. I would always start with the 0 because that's easier. Plug in a 3. So when you plug in a 3 in for t, you're going to get 175 out. Now here's where I would go to the calculator. Now it'd be nice. I mean, it's good to know to be able to solve these these e functions without a calculator. But on this problem, you'll be able to use your calculator. So you would simply go to menu, algebra in your calculator section, menu, algebra, solve. I would just type that in just like that. And then you got to do comma k, right? If you're going to put a k in there, comma k. You got to tell what you're solving for. Now it's going to give you the answer in LNs. So I would do a control enter so you can get a decimal. All right. So you really don't need anything after that line except the answer. Now you said that was 5-1 something. 0. Okay. And I would write down a number of those because we're going to use this in a later calculation. Yes, Eric. That is inside the parentheses. The vertical bar was always outside the solve parentheses. If we needed to limit our domain, that was mostly in trig functions. We don't have to here. But yeah, the comma k is inside the solve parentheses. Yes, good question. So we're going to solve that equation. It gives us k as that value right there. Now what? So basically we have a new equation. Our equation is y equals 70 plus 120 e to the negative 0.4. Is that 0.4? Am I missing a 0 there? I'm missing a 0, aren't I? 0.4451. Yes, I thought. Okay, 5-1, 0. So it's that first one. I can give somebody an extra one tomorrow. I can put it on the website.
Okay, that would be great.
Yeah, I'll put a PDF of it on the website for sure. Okay. All right. So we've got this, and whoops, and then there's a T there. Sorry, ran out of room. And now we plug a 6 into there. So we just take a 6, plug it in, and what are you getting? 160. 161. And we'd want to go 3 decimal places. So let's go 875, unless it said differently, and it might. On a problem like this, it might say 1 decimal place. 100, and that makes sense. After 3 minutes, it went down 15 degrees. After 3 more minutes, it would go less than 15 because it is leveling off. It's starting to cool a little slower. So it didn't go quite 15 degrees in the next 3 minutes. So that seems like a reasonable answer. It's a 161. I can't believe you can't read that.
It looks like a question mark in an exclamation point.
161.875 degrees. So there, again, the stuff in blue, there's really no calculus there, right? I mean, that's just function notation, plugging numbers in, solving equations, right? We can use our calculator to help us along the way. The calculus is, hey, this is a differential equation. The solution to that differential equation is this, which tells us the temperature of the coffee, and now we can use that solution to do some stuff. Okay? And then then the whole point of differential equations, initial value problems, is you have some initial condition. Once you know the solution, you can plug it in to find your constants. Remember, there's always plus C's or A's or K's or something in there, and then we can find those. So you're going to get a lot of practice at that on your homework. You've got a bunch of the matching that we just talked about, and you've also got 23 and 24. If you notice on that homework line, 23 and 24 are where you're going to spend most of your time. They're both these kind of problems. Okay, one of them is 23 especially has a lot. You're going to calculate stuff like this 4 different times because they're going to give you a situation where the coffee is outside and there's 2 different cups. So they have 2 different K values. One is styrofoam, one is cardboard, so they insulate differently. So they have different K values. Then you're going to move the coffee inside and recalculate. So you have a different room temperature. And so you're going to get practice at doing this. You're going to have to be able to do this stuff right here on our next quiz for sure. All right, now, last thing, and then I'll let you work. On that 2011 free response thing, grab that packet again, and we're going to look at number 5 real quick. Eventually, we will do all of this packet, or at least as much as we can do before the midterm. So there will be some more problems we'll finish on this. But I want to look at number 5.
Mr. Clark,
Yes. Yes.
on that last one, I got my decimal moves a little bit different. Is that just a setting on my calculator?
Yeah, I wouldn't think so.
Are you in degrees?
Because I got 0.8.
That could be when you if you used a little more of a rounded value for your K. Yeah, you put 0.445. Probably want to use a few more decimals when you put the K back in. All right, number 5. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W is the total amount of waste at the landfill. Planners estimate W will satisfy this differential equation for the next 20 years. W is measured in tons and T is measured in years starting at 2010. Here's my question to you. Does this differential equation right here look familiar? What's it look like? Isn't it Newton's law of cooling? I mean, look back at your notes here. Newton's law of cooling was Y prime equals K times Y minus big T. Now, this clearly is not a cooling problem, but it doesn't have to be a cooling problem. T is just a constant. K is a constant. Y has to match the Y prime here. Well, look what you got. You got W prime. You got your K. You got W minus some constant. This is Newton's law of cooling. Now, later in the year, we will learn how to just solve this differential equation. In C, they want us to find the solution to this differential equation. Well, I would say to you that if you've already memorized this as Newton's law of cooling, you can save yourself the work of solving. Okay? And we now know Newton's law of cooling. And so, for this problem, I can just write W equals, tell me what to put here. You might have to look at your notes there for Newton's law of cooling. We haven't memorized it maybe yet.
T 300
The solution is the big T, which would be the 300.
plus
A, E, 1/25th, T, right? Because K is 1/25th, and that's 300. What we don't know is the A. Did they tell us anything in the problem that would help us get that? Oh, that was nice of them. Boy, the AP test, they sure make things easy for you. They even gave you that. Why would they have to give you that? It was right there and there. Well, they're nice or not. They told you right here that at the beginning, in 2010, there's 1,400 tons of waste. So that's W. That's initial condition. But they wrote it there, and that's not. So if I put a 0 in for T, this, of course, would be e to the 0, which is 1. So what would A be? No, we put 1,400 over here. So 1,100. We'd subtract 300. So you'd put a 0 in here. E to the 0 is 1. We'd have A plus 300 equals 1,400. So A would have to be 1,100. So there would be our equation right there. Our equation, our particular solution to that differential equation would be W equals 300 plus 1,100 e to the 1/25th T. Okay, so that would be our work for part C. All right, now you might have forgotten that, or might not have recognized that that's Newton's law of cooling. We will learn how we can actually solve that. That's one of them we'll learn how to solve later on. Okay, and then like B says, find this. What's d2w over dt2? What's that mean? No, just means second derivative. That's w double prime. That's weird to say. That'd be w double prime. Be the second derivative. Well, here's w, so you can do the derivative once to get double prime and do the derivative again to get the second derivative, right? You wouldn't have, oh no, I'm sorry, we wouldn't do that because they want it in terms of w. So you'd actually do the derivative, we would do that derivative up here. We'll talk about how you would do that as well. It'd be like an implicit differentiation, right? When we do the derivative, we tack on a w prime and so forth. So I don't want to get into that right now. And this one's another tangent line one. And we get into some things there. But I just wanted to show you how this, like Newton's law of cooling, is a special differential equation that sometimes comes up. And here it was on the AP test a couple years back. All right, so your homework is that top line of the on the work. 3, 4, and 5 are kind of interesting, so maybe I'll just do number 3 with you to help you get started here. So you have 3, 4, 5, 6. 3, 4, 5, 6 are all kind of the same. And then 7 through 14 is the matching. And then 23 and 24 is the Newton's law of cooling. And that's what you need to be able to do for today. So, number 3. And again, 3, 4, 5, and 6 are all essentially the same kind of problem, but they're each worded just a little bit differently. And I want you to be able to do this. I don't like really the way they worded these questions necessarily. On 3 it says, they give you a differential equation, and then they say, and I don't know why they use f and y, so f and y are the same thing. And then they say, explain why this is an equation of the tangent line. Well, that makes you think, explain why that's the equation of the tangent line, like you have to do a t-chart or show. I think you just pretend that the question said, find the equation of the tangent line. And just go through that work, and then that will show that it is. Okay, instead of explain why this is the equation of the tangent line, just pretend it said, find the equation of the tangent line. So, here's what they told you. They told you that y prime equaled t squared, what was it, t squared y plus t. So they gave you that. And they want you to find the equation of the tangent line at the point, what? 1, 2. So what that means, and I'm going to use y instead of f. I'm not sure why they mixed up y and f there. So they give you the point 1, 2, because right, what have we always said? If you want the equation of the tangent line, you need point, you need slope. You need point, you need slope. So y of 1 is 2, and y prime of 1 is the other thing we need. All right? So how can we get y prime of 1? Well, actually, we're not only going to have to plug 1 in, we're going to have to plug in the 2, right? So for the t, we'll plug in a 1, and for the y, we'll plug in a 2, because that's what happens on differential equations. You have both x and y in them sometimes. So if we want the equation of tangent line to point 1, 2, we might have to plug both points in. So we get 1 times 2 is 2, 2 plus 1 is 3. So that's our slope, right? Because that came from the differential equation, which is y prime. Well, now we got what we need. So all we do then is we go, okay, that'd be the slope, 3 t minus 1 plus 2. We just take our point and our slope and plug it in. And now normally we could stop there. If it just said find the equation of the tangent line, this one said show that the equation of the tangent line is this other thing. So let's go ahead and finish it. Let's go ahead and distribute. And sure enough, there it is, right? So I just showed, or I just explained right there why 3t minus 1 is the equation of the tangent line. Not the solution of the differential equation, so don't confuse that. I know we got a y here, but that's we didn't find the solution of the differential equation. We found the tangent line on the original function after point 1, 2. All right, so do that for 4, do that for 5, do that for 6. It's practice plugging into differential equations, understanding that that tells you slope, and then using it in a problem like that. All right, rest of the time is yours.